Great. So I'm excited to have two of our marketplace data partners joining us today for the webinar. They're going to talk all about the cool data sets that they have available through the marketplace. And we are going to start with Hansi Singh, Dr. Hansi Singh, CEO and founder of Planette, to talk about their seasonal to subseasonal forecasts. So take it away, Hansi.
Thank you for the intro, Ryan. Really excited to be here. So today I'm going to talk a little bit about our hybrid physics AI long range forecasts, subseasonal to seasonal, 1 week to 6 months lead time. Our data sets, we are Planette AI. We are a National Science Foundation and NASA portfolio company. We use science to extend the range of forecasting to produce accurate quality forecasts at these lead times that many, folks have these lead times as an afterthought. Just a quick intro on who I am. So I'm an Earth system scientist. I used to be a fellow at the Department of Energy. I also used to be a prof. I'm still a working group co-chair at one of the major working groups of the Community Earth System model. So I still have a hand in some model development today. But most of what I do is try to take the latest in science and make it actionable for real world use cases. And hence, that's why it now lives in part on the Earthmover marketplace. So I'm going to first talk a bit about the science of long-range weather forecasting, a bit about Earth system modeling, a little bit of background on our hybrid physics AI forecast methods, and then some details on the forecast that we have available on the marketplace. So just to, kind of start on this, I'll go pretty fast. So the big problem in weather prediction is that we want to take an initial state of today, apply physics to it, and produce a final state for tomorrow or however many days into the future. And so traditionally how this is done is through an atmospheric model, also known as a numerical weather model. It is a very complex model, usually tens of thousands of lines of code that have a lot of details of how the atmosphere functions, a lot of different equations. And an example of this is WRF. And so it is a model that is able to tell us how the weather evolves over the next few days. Now, why can't we use this model beyond a few days? Well, so this is kind of generally the workflow. Why can't we use this beyond a few days? The reason why is because initial conditions are always uncertain and the atmosphere is chaotic and it has a particular exponent that defines that chaos, which I'll talk about. So essentially what that means is that if you start at some initial condition, your trajectories diverge in time, and so your forecast becomes inherently uncertain, and all forecasts are probabilistic. For the atmosphere, this kind of divergence happens completely after a couple of weeks. So this is why your weather forecasts are limited to 10 to 14 days. So just using an atmospheric model is not going to get you really good predictability beyond the 14-day, 10-day time horizon. So in order to predict anything in the Earth system beyond, that 10 or 14-day time horizon, we really need other parts of the Earth system because these provide memory beyond that 2 week horizon. So the atmosphere has days of memory. The land surface can provide weeks, months, even years of memory. Ice can provide months to years, and the ocean can provide years to decades to centuries to even millennia of memory. It's very exciting. And so, what this means is that we need a much more complex modeling framework in order to capture the way that the Earth system evolves over these longer time horizons. But thankfully, there are parts of the Earth system that allow us to have predictability. And so what we use are Earth system models. And so Earth system models are, we call them fully coupled models or kitchen sink models because we have everything and the kitchen sink in them. Atmosphere, ocean, ice, land, thousands of equations. The community Earth system model has over, I think, 2 million lines of code in its latest incarnation. There are a bunch of examples of these models. Different models have strengths and weaknesses, et cetera. The really cool thing is that there was a Nobel Prize recently won for this kind of modeling. So Suki Manabe at GFDL was one of the winners of the Nobel Prize because he was one of the groundbreaking folks that put together these models and was able to run them and get a decent climate state for, today and into the future. So, how we generate long range forecasts is that we take an Earth system model, we initialize it with a bunch of initial conditions, including not only the atmosphere, but also the ocean, the land surface, and the ice. And from this, we produce an ensemble that is our long range forecast. And so, when I say ensemble, many different realizations of the future. And so, the real takeaway here is that if we want anything beyond our 7 day or 10 day or 14 day weather, we really need a more complex modeling framework. So the area that we focus in is really subseasonal and seasonal. With long range forecasting, we can even get to, interdecadal to decadal. But, we don't really do that because most of real world users seem less interested in this and much more interested in this. And of course, with Earth system models, as I think Kevin is going to talk to you about in a little bit, we can really look far into the future and really get an understanding of the trajectory of the Earth system over decades, even centuries, potentially. So, how do we do what we do particularly? What is our sort of secret to producing forecasts that have better skill, much better skill than what you can get publicly? So, what we do is we combine various input streams from physics-based models with our own in-house AI model, which we train actually on Earth system model data. All of these are, of course, initialized models, and they produce forecasts over weeks to months. And what we do is we then combine them through an AI calibration and merging algorithm. And by doing this, we are essentially able to construct a forecast that, based on the past history of that particular model, has maximum skill. And so from doing that, we are able to forecast variables like temperature and precipitation, which is what is available on the Earthmover marketplace today. And we also have many more variables as well. So if you're interested in any of those, let us know. And yeah, we will put them on the marketplace as soon as we can. So, what does this buy us in terms of performance metrics to do this kind of hybrid physics and AI approach? So, on the right here is the anomaly correlation coefficient, specifically for wind at 1 month lead time, so 30 to 60 days. This is the CEAS-5, the best seasonal forecasting model in the world. It's basically IFS with an ocean and ice. And this is our hybrid physics AI model. Our ACC is close to 100% better. And so, we really are able to increase the skill of what is available state of the art to you. So that is our value proposition, that we are just forecasting the future better. And maybe this helps you make better decisions in your company. Maybe this helps you trade better. Maybe this helps you hedge better. Yeah, more accurate information on the future, of course, can be valuable in so many different ways. And I chose wind in particular because this is always feels like a little bit of a niche variable to people. And yet, for example, the Texas grid has a huge amount of wind, right? So if you're trading in Texas, like you really want to know what's going on with, their wind turbines and the availability of wind energy. And so we can really help you with those questions to get a better sense of what the range of possibility is given initial conditions today. So this is just like kind of a little overview of just how fun seasonal forecasts are. I just love them. So we have an El Nino on the way. So here I'm like showing, the late summer to early fall. And it's just like, I mean, El Nino always has like such strong, amazing impacts. And I know in some areas of the world, of course, like these are very serious impacts. Like, for example, you can see kind of huge droughts over Southeast Asia and South Asia, parts of the Sahel, some interesting signals emerging over Southern Europe. So yeah, this is kind of the magic of long range forecasts. We can just look much deeper into the future than we ordinarily think of when it comes to weather forecasting. And so here's some specs on our forecasts. We go, as I said, up to 6 months. We update them every day. We have many available variables. You can check out temperature and precipitation right on the Earthmover marketplace. If there's any variables that you're interested in and we don't have, just contact us and let us know. And, chances are we might have it already or that it is relatively straightforward to add. And so keep in mind that all forecasts are probabilistic. So we provide you expectation values, but we also provide you with the full probability distribution, the fifth to 95th percentile. And yeah, this is obviously on a latitude longitude grid, and it is 25 kilometers resolution. And if you're interested, we have 8 years of out of sample back tests. And so we can provide those to you if you are very interested in become a client of ours. So thank you so much. Really excited to be part of this and excited to have an opportunity to be a partner with Earthmover on their marketplace. And so, yeah, just very excited to get this data out there to the folks that are using this great tool. Thank you so much.
Cool. I'll ask one follow-up question, Hansi. I'm just curious about what's the how do you recommend people like evaluate the forecasts, right? So say they're interested in exploring them and trialing them. Like what's a process that works for people to see the value that they can get from the forecast? Like, do you have archives that you can share, like, and methodologies you can recommend?
Yeah, absolutely. So, as I mentioned, we have those 8 years of comprehensive back tests. We also have our own, like, kind of statistical methods where we have evaluated various forecast metrics. And so, our goal really is for some customers who might want to, actually have the full 8 years. Usually, we found that 8 years feels overwhelming. So, people will ask for, like, hey, can you provide back tests for the last couple years? And then they will kind of do their own sort of internal analysis based on that. So we just are very flexible in terms of how we can, provide data to folks in terms of that evaluation process, what that evaluation process looks like to them.
Cool. All right. Thanks a lot, Hansi. Really appreciate it. Actually, I learned a lot from your presentation. Excited to see what the El Nino is going to do also for next year. And I'm trying to plan my ski trip for next winter. So I think I need to be looking at some of your forecasts to make that decision.
Yeah, yeah, definitely, definitely. Yeah, there's some areas that you probably want to avoid. So.
Cool. Okay, let's move to our next speaker. So we have Dr. Kevin Schwarzwald of Columbia University here to talk about their new bias-corrected downscaled climate data set. So Kevin, take it away.
Yeah, absolutely. Thank you so much, Ryan, for having us on and for giving us the opportunity to get this data out there to a lot of people who wouldn't have access to it otherwise. So, yeah, like Ryan said, I'm Kevin from the Climate Uncertainty Lab, and I'll talk to you guys about a data set we just released through Earthmover that we're really excited about, the bias-corrected downscaled massive ensemble. Just a quick summary of who we are. We're statisticians, climate scientists, and economists at Columbia, at the Columbia's New Climate School, and also Colorado School of Mines and the Business School. And really, so we work on figuring out what the range of future climate risk is going to be. And we create tools and data sets to make understanding and constraining that uncertainty easier. And we work with users of climate data to make sure that the people and the organizations working to prepare us for the impacts of climate change actually have all the knowledge they need to truly anticipate future risks. So let me motivate what I'm going to be talking about today in this data set, the bias correct and downscaled massive ensemble, by a question that's currently near and dear to my heart after we had this crazy heat wave in New York last week, which is what if we want to know how many days are going to reach 80 degrees Fahrenheit in New York City in the future? This is personal to me because that's roughly when we really have to start using the AC, but 80 degrees is also a threshold that California uses for worker heat safety standards, for example. So has a lot of implications beyond just my annoyance at the heat. And so historically, we've had about, 60-ish days a year that reach 80 degrees in New York. And we want to know what's happening, how that will change in, say, a couple of decades. And so when we try to figure out these longer term types of information, like Hansi just told us, we move away from the world of numerical weather prediction and into climate modeling, longer term climate modeling, for which we have these things called global climate models, which are we put in all of our information that we know about physics, about chemistry, increasingly about biology. We put in the continents where they are in the real world, and then we spin it up for a simulation of how the Earth's atmosphere and oceans and everything else are actually evolving. And of course, the most important thing about these climate models is that they give us the knobs to test how our human actions are going to affect the climate on longer timescales through CO2, through land use, through aerosols. And so if we want to know how the climate is going to change, uh, let's say here, what I'm showing you is just a pattern of change in temperature at the surface most everywhere on the globe. And we can figure out what would happen if we emitted more CO2, changed land uses more, or emitted more aerosols, for example. And so the first thing that's important about this is that this means that there's not just one future climate projection. It's a bit of a truism, but there's uncertainty in this whole system. And the first set of uncertainty just comes from what's actually happening on the human side. How much CO2 are we outputting? How many aerosols are we putting into this world? Which is something that climate scientists call scenario uncertainty. Next, we have this thing called model uncertainty, which is that there isn't just one climate model. There's actually about 40, 50 of them out there in the world. They all make slightly different decisions and priorities on how they model this incredibly, incredibly complex system. And so if we ask the Access ESM15 model, which is an Australian model, it's going to give us a different answer to how the Earth is going to change, even with the same CO2 forcings, than if we ask, for example, can ESM5 or another one or another one or another one until we have about, a dozens or more estimates of what the future will look like just based on these different climate models. But then finally, even if we weren't changing anything about the system, if we were keeping CO2 constant, we were keeping aerosols constant, we weren't doing anything to the land, we would still have cold years, hot years, and the El Nino, the coming possibly monster El Nino, we'll see what actually happens, that Hansi and Ryan just brought up is just one large scale example of what we in climate science is called internal variability. So the uncertainty that just comes from the fact that the Earth can park a lot of energy in one part of the world or another part of the world without really changing anything about the overall climate on average. But there's one other wrinkle that comes when we're actually trying to figure out, when we're trying to translate what these climate models are telling us to usable information we can plug into climate risk models. And this is that climate models are pretty coarse. This is a grid, a typical climate grid that I've imposed over New York City right now. You can see there's a pixel that takes over most of Long Island and half of the ocean right above it or right below it. And also, climate models are biased, which means that they're not perfect representations of the real world. None of them are. And it means that to get the numbers to actually make sense in our climate impact models that we're training on historical observations, we need to adjust the output from that. And so, to get from this coarse, biased world to a less biased, high resolution world, we need historical climate observations as ground truth, historical weather records. And this is actually a lot more complicated than you may think. The Global Observational Network is kind of sparse. This is just a map of where we have weather stations that report to these global products that we use. And there are, of course, a lot of gaps in developing countries in the tropics. But even in the rich world, the density of the stations, the number of weather stations that we have, has been declining over the last couple of decades. And so what we do to plug these gaps is we use these things called reanalyses, which are computer models. They're honestly kind of high resolution climate models, but they're constrained by observations from weather stations, from satellites, from airplanes, from radar. And like the climate models, there's more than one out there that are making different decisions out there about how to model this, which results in its own uncertainty about what the real climate actually was over the last couple of decades. We've been calling this observational uncertainty. And does any of this matter? How much do these matter for a particular problem? Going back to this motivational example of how many days over 80 degrees Fahrenheit are we going to have in New York City in the future, let's think about what would happen in a Paris Agreement world, a world that is 2 degrees warmer than pre-industrial, and then figure out how much of these different sources of uncertainty contribute to figuring out how many days at a particular temperature we're going to have. So there's model uncertainty. It's honestly, for this particular problem, not that important. There's internal variability, which is about 2 to 3 times as important for this case. Um, and then finally, there's the choice of your historical ground truth that you're basing all of this on and that you're defining these temperatures for, which in this case for New York is actually the most important thing that you have to decide upon. And that is really the motivation behind creating this data set, because whatever you're estimating into the future, whatever you're projecting, if you care about the spread, if you care about the true underlying distribution of risk that you may be exposed to, you need information and data sets that account for all of these sources of uncertainty, which unfortunately current products don't always do. Scenario uncertainty, model uncertainty are pretty commonly accounted for in things like NASA's Next GDP or EasyMap or Carbon Plan or GDPCIR. But there are very few products out there that actually take into account this internal variability, and no global products, to my knowledge at least, that actually let you think about the impact that your choice of historical ground truths have on your projections. And so that's why we built the BCD-ME. But how do we sample these? I will cover this very briefly in a second. We abstract away from scenarios by showing everything at global warming levels. Um, we use many different GCMs to get at the model uncertainty. We use many different, we call runs or ensemble members per GCM. What climate modelers do is they let basically a butterfly flap its wings inside the model and then see how that changes things without changing any of the inputs. It gets you an idea of the true internal spread of that. And then finally, we bias correct and we downscale to 4 different reanalyses, which means you can really think about which ground truth is actually most trustworthy for your needs. And all of this put together gives us about 1,400 future bias correct and downscale projections of temperature and maximum temperature. And this is what this looks like. Here's just a random sampling, a random draws from a couple of different simulations for the climate change, the change in mean temperature at the surface for in a Paris Agreement world versus the late 20th century. And I really hope to give you a bit of an idea of how different each of these frames are. And what this means is this is the real spread that's implicit whenever you use any sort of product to get at future climate projections, is that whether or not they sample this uncertainty, it is there and it is underlying it. So going finally back to this motivating question, how many days above 80 degrees Fahrenheit will we have in New York in the future? If we ask the BCDME at 1.5 degrees, we should expect on average maybe 70 days or more. If we go to 2 degrees, we might expect even 80 or more. And with some outliers up here saying that we might actually have 120 days or more on average that are that hot in New York. But the real strength of the BCDME is not just to give you this average signal, but to actually let you split it up and figure out where is that coming from. And so in this case, most of it is actually coming from what are you choosing as your ground truth? Do you think the Era 5 reanalysis is going to be the most accurate for your metric or what you're looking at, or are you looking at GMFD instead, which is the one that NASA Next GDP, for example, uses? And this choice is going to actually end up determining, in this case, how many days we should expect. And it's only the BCDME that can really kind of, to my knowledge at least, that allows you to test this really easily. So I mentioned that we show all of our data on global warming levels instead of by year. We have a couple of reasons for that. One is that it allows us to better sample internal variability by pooling runs across different scenarios. It lets us avoid the hot model problem. I don't know if you may have heard about it. Basically, when the CMIP 6, the newest generation of climate models came about, a few of them were determined to be probably unrealistically fast in their warming. And this really lets you just kind of normalize for that and still use information from them. And also, it allows users to bring in their own scenarios. This is common, for example, in the climate stress testing that international financial institutions do. They do this stress testing at global warming levels. You can figure out, bring in your own kind of ideas of which policies you think are going to happen in the future. You can use IAMs such as FAIR. You can think about results in terms of a Paris Agreement world, and it really gives the user flexibility to go beyond just the scenarios that are imposed by how these models are run through CMIP. So, in short, this is a kind of quick run through of this bias correct and downscaled massive ensemble. We built it because we wanted to get a better idea of the climate uncertainties in our own projections, and we hope that it can help other people do the same thing and really account for model uncertainty, internal variability, observational uncertainty, and bring in your own scenarios to figure out how your own risks are changing. We have a preprint up here. This also has a sample code that explains what the structure of the data set is on Earthmover, and also just some of the trade-offs that went into building this data set. It's currently under review, under peer review, but that'll give you kind of any of the technical details that you'd want to do, that you want to know, and in addition to some guides on how to access the data. So yeah, we're really grateful to Ryan and the Earthmover team for letting us share this. This is 100 terabytes of data that would not have been feasible for single climate scientists to be able to make really cool science and analysis with in a short period of time until these kinds of structures and these kinds of infrastructure was built up. And so I think it's going to make it a lot easier to actually get a good sense of what the spread of future risks are than was possible before. So.
Okay. Thank you so much, Kevin. I really learned a lot from your webinar as well. I like have one question, um, which I'll just throw at you. Help us understand like the range of use cases for downscaled climate data. Like obviously it's important and interesting from a research point of view, but like what are some of the different sectors, in private sector that might be able to benefit from this type of information?
Yes, absolutely. So when we downscale this information, it's finally back at kind of the scale that we're used to actually experiencing. This quarter degree resolution is similar to what Planette is using in their forecasts. And it means what you're getting out of the BCDME is temperatures that are realistic and that are comparable to the ones we experience in a particular location instead of these kind of abstract averages over large spaces. So that means if you care about temperature or maximum temperature, these are the variables we have right now. Hopefully, we'll be able to expand this kind of in the future as well. And some examples might be you're worried about uh, worker heat exposure in the future, or you're worried about the efficiency of your solar panels in hot temperatures. You're worried about kind of, yeah, whether your electricity networks are going to be able to handle the increased demand from ACs. In all those situations, you really need this kind of directly comparable localized information that you can't get straight out of the climate models at the large scale. And so that's the kind of some of the things that we're hoping that people are able to get from this product that they would not be able to otherwise. Mhm.
Awesome. All right. Well, thank you, Kevin. I think we can stop the recording.